Okay, what if I told you that the steady tick-tock of a clock, the one thing we all think of as an absolute constant, isn't constant at all? What if, for someone moving crazy fast, time itself actually slows down? Well, today we are going to completely shatter that illusion of absolute time by diving headfirst into the seriously weird world of high-speed physics. And our guide for this little journey into the bizarre is a fantastic thought experiment from Chapter 10 of the book Newton and Relativity. So we're basically going to use their setup to figure out exactly where our everyday, common sense intuition about how the universe works just completely goes off the rails. See, for most of human history, speed was simple. You're on a train going 50 miles an hour. You throw a ball forward at 10, somebody on the ground sees it moving at 60. You just add them up. But when you start getting close to the speed of light, that simple math, it just breaks. And this failure has a couple of really profound consequences. First, it means we have to find totally new rules, new math. And second, and way more importantly, it forces us to investigate the very nature of time itself. So how in the world do you investigate something like that? Well, we're going to head to a particle accelerator, or, a thought experiment version of one. We're going to set the stage for a super high-speed collision and see exactly where the old rules lead us astray. So picture this. Inside a giant machine called a synchrotron, we've got two tiny particles, and they're being accelerated, just hurtling towards each other at almost the speed of light. They are just about to zip into a detector of a specific length. We'll just call it L, and that's where they're finally going to collide. Now, to make any sense of this, we need a couple of different points of view. So let's meet our two key players. First, you've got Observer Ol, who's just standing still, watching from the laboratory. And then there's Observer O, who gets the wild ride literally moving with one of the particles. And their mission? It's exactly the same. Calculate the precise amount of time that passes from when the particles enter the detector to the very moment they smash into each other. Okay, but before our observers even think about starting their stopwatches, they're both working with two common sense rules from classical mechanics. These are assumptions that honestly we all take for granted every single day of our lives. Think of these assumptions like the two main pillars of how we think the world works. The first one is the invariance of lengths. It seems totally obvious, right? The detector is a certain length, and both Ol and O should agree on what that length is. A meter is a meter. The second pillar is the invariance of simultaneity. This just means both observers agree that the two particles enter the detector at the exact same instant. Seems unshakable, but these two ideas are about to create a massive contradiction. Because when our two observers apply these perfectly reasonable common sense rules to this high-speed situation, they run smack into a paradox in time. The math just completely stops adding up. All right, let's start with Observer Ol, our friend just chilling in the lab. For him, the calculation is super straightforward. The particles have the same speed, right? So they're going to collide precisely in the middle of the detector. The time until that happens is just the distance one particle travels, so that's half the length of the detector, divided by its velocity. Simple? Easy. But now, let's jump into the shoes, or I guess the reference frame, of Observer O. From their point of view, they are the one who's stationary. It's the detector and the other particle that are rushing towards them. Now, to calculate the closing speed of that other particle, they can't just add the velocities like we did with the train. They have to use this more complicated beast called the relativistic velocity addition formula. And here it is. This is the whole problem in a nutshell. The two formulas spit out two totally different answers. The time calculated by Ollie is fundamentally not equal to the time calculated by O. I mean, think about that. They are watching the exact same physical event, but their stopwatches are showing completely different results. How is that possible? And let's be clear, this isn't just some quirky math problem. It's a physical impossibility. A collision is a real thing. It has to happen at one specific spot. But if Ole's time measurement is different, that implies the collision doesn't happen in the middle of the detector from their point of view. It means the event would literally happen in two different places at once, which, no, that can't happen in our universe. So something's gotta give. One of our common sense assumptions has to be wrong. And the solution, the way out of this paradox, requires us to do something pretty radical. We have to shatter the idea of absolute simultaneity. The math shows that there's no way around it. The only way to make the physics actually work is to take a sledgehammer to one of those pillars we talked about earlier. And the one that has to come crumbling down is the invariance of simultaneity. The problem isn't our clocks. It's our basic assumption that at the same time means the same thing for everybody, everywhere. And this leads us to a truly mind-bending conclusion. For observer O, the one riding along with the particle, the two particles do not enter the detector at the same time. What is simultaneous for our observer in the lab is not simultaneous for our observer on the move. Simultaneity, it turns out, is relative. It all depends on your frame of reference. And there it is. This is the proof, the confirmation of a cornerstone of relativity, the existence of local time. Newton's beautiful, elegant idea of a single universal clock just ticking away for the entire cosmos. It's wrong. It's simply untenable. Time isn't some absolute backdrop for events. It's an active player in the game, and it is inextricably linked to velocity. So this isn't just some weird idea from a thought experiment, okay? It has real, tangible, and frankly, bizarre consequences. Let's take a look at how this idea builds into the reality of relativity, with effects we can actually see and measure. This table here lays out the whole paradigm shift perfectly. On one side, you've got the classical world of Newton. Simple velocity addition, absolute simultaneity, one universal time, and fixed lengths. And on the other side, you've got the relativistic universe, a new formula for velocity, relative simultaneity, local time, and, get this, lengths that actually contract. Yeah, you heard that right. One of the wildest consequences of all this is something called length contraction. If you're observer all and you're watching a proton zoom past you at an insane speed, it doesn't just look squished. From your frame of reference, it is physically compressed into a pancake shape in its direction of motion. This is not an illusion. It is a real physical effect. And we don't have to just imagine this. At places like the Large Hadron Collider at CERN, physicists deal with this every single day. They accelerate protons to 99.9999991% of the speed of light. And at that kind of energy, the proton is flattened to almost zero thickness in its direction of travel. This is not science fiction, folks. This is engineered reality. So, where does that leave us? Well, we've just completed the absolutely crucial first step. We've used pure logic to prove that time has to be local, and simultaneity has to be relative. The next step on this journey is to use the one thing that is constant, the speed of light, to find the exact formulas, which will eventually let us derive the famous Lorentz transformations. Those are the mathematical keys that unlock this whole relativistic universe. And that leaves us with one final fascinating question to just chew on. We just took apart one of the most fundamental truths we have, the absolute nature of time. So, if time itself can change with speed, what other absolute truths about our universe might just be a matter of perspective?